for the really warm welcome, and yeah, thank you all for coming. Yeah, so detecting chains. What are chains? These are chains. Today I'll be talking about how at Yelp we leverage our business data to discover all the chain businesses that exist out there, and how we use Spark and machine learning to do just that. So, quick intro about myself. I'm Andrew. I've been at Yelp for about 4 years. I'm educated by the University of Toronto. That's in Toronto. Any Torontonians get that joke? Okay. Anyway, being Canadian, I do pretty stereotypical Canadian things like hockey and snowboarding. And since this is a talk about chains, I figure I should give a shout out to one of my favorite chains, which is Crispy Crunchy Chicken, which is like Popeyes, but like more underground. They exist exclusively in convenience stores, and it tastes particularly good at 3 in the morning. So in this talk, we're going to learn how we actually detect chains. And since migration seems to be a pretty popular theme in the talks here, we'll talk about our wins from moving from Redshift to Spark. And lastly, you should get some insight on how to integrate Spark into your existing Python application. So first, why do we want to detect chains? Well, we can do a lot with this kind of data. It can help us do personalized recommendations for users, for example. We can have a special UI to search for chains, like we see here in the screenshot. And we can plot them on a map and show them to a user. And I personally love this feature because I don't know about other Californians here, but I'm constantly looking for the nearest In-N-Out. There never seems to be one nearby. And yeah. And we can also learn what topics users are generally discussing across all the businesses in a chain. So hypothetically speaking, maybe the reviewers for In-N-Out are talking about how good the ingredients are, or how good the quality ingredients, or the good service, and maybe McDonald's reviewers are talking about how much they miss the McRib, or we can kind of infer these topics from the reviews. So to get this chain data, we have a system called Chain Detector. And our task is to get something like this. So for each chain, we have its name, its URL, and the business IDs associated with it. And here's our input data. So this seems pretty straightforward, right? We have a bunch of Starbucks businesses, McDonald's businesses, we have walk and roll. So all we need to do is group these by their name, and we're done. Pretty easy, right? Yeah. So it kind of lied. Data often doesn't look that perfect. That is, it doesn't readily exist in a very consistent format. We have Starbucks and Starbucks Coffee. Which one is the right name? We have inconsistent URLs. And the URLs don't even correspond with each other. We have starbuckscoffee.com with Starbucks, and we have starbucks.com with Starbucks Coffee. So there's kind of this misalignment there. There's inconsistent punctuation. There's missing data as well. And that walk and roll right there, that's not even a chain. We call that a cliche. So suddenly this became really non-trivial. So let's walk through how Chain Detector handles some of these problems. Well, first we're going to do some hella preprocessing. The goal here is to get our data in a consistent form. So we can normalize business names, remove capitalization, punctuation, even unnecessary suffixes like incorporated that don't actually add any meaning to the business name. So we can get a common representation of the names of the businesses. Similarly with the URL, we observe that the only important component of the URL is the domain itself. And the next step, we're going to do kind of what we suggested before. We'll create these chain groups of these normalized tokens, which we'll call the naive candidates. And then we'll merge the groups that are similar. And we'll see an example of this soon. The last stage involves a machine learning classifier, which helps us deal with things like cliche businesses. So let's see what happens with our toy data set. So after some pre-processing, we have a more common representation of the names and the URLs. And our job has become a little easier, right? But we still have this problem with some missing data and some name and URL inconsistencies. So let's focus on what happens with like these Starbucks businesses. So with those 3 businesses, we have created 4 token groups, one for each unique name and each unique URL. So all the businesses whose name normalized to Starbucks are in C1. All businesses whose name normalized to Starbucks Coffee are in C2. And all businesses whose URL normalized to starbucks.com are in C3, and so on. And so these are naive chains because we have like a lot of duplicates here, and like this isn't very good. So these are just like, you know, a starting group of chains. So that's why we're going to merge these. So as you can see, C2 completely overlaps with C3. So let's merge it. And then our new C3 largely overlaps with C1. So we'll merge these as well. And this is what we're left with. Now it's kind of clear to see which is the most common name and the most common URL for this group of businesses, and then we can use that name and URL in our final chains data set. Our classification stage involves a combination of a linear discriminant analysis classifier and a random forest classifier that we trained offline with many examples of true and false chain data. This helps deal with chains that have common names like cliche businesses, as you saw before. It also helps with generic names like Henry's Restaurant. And what I want you to observe is that like these aren't really the same thing. Like Walk and Roll is, or Taste of China is not generic in the same way like Pizza Slice Houses or something. You know, it's kind of like a name, but like they're not like really generic words all put together. And this is what our classifier tries to deal with. So let's see some examples in our classification stage. Here we have many features to help us distinguish actual chains from false positives. The term frequency map is how often each term appears in the chain. So 10 businesses have the name Starbucks and 2 have Starbucks Coffee. And we do the same thing for the URLs, the categories, the states. The geocenter is the average latitude and longitude of all the businesses in this candidate. And that's how we're going to get our next feature. How far is each business from the center? Because we expect a certain distribution of these distances. As you might imagine, most chains originate from a certain region. Like if you're on the East Coast and you're like, why isn't there like an In-N-Out here? Like it turned, you know, so In-N-Out basically is only in California, originated here, and you know, Shake Shack started in the East Coast and it's kind of like branched out from there. So like, it's not a random distribution. So with this chain, you know, we have a high ratio of similar terms, URLs, categories, small distances to the geocenter. So this is likely to be a chain. So is this a chain? Again, we have a high term similarity ratio. All businesses have the same name. So far, so good. But it's pretty low for URLs. Because most businesses in this candidate don't have a URL, maybe because they're all like locally owned businesses, they don't have websites. Some cluster analysis of these distances to the center may appear sporadic. They don't follow a typical distribution of a chain business. So maybe this is less likely to be a chain. So that's a bit of an overview of the application pipeline. Let's like step back a bit to like a bit of the architecture. So this is a bit of what the stack looks like. Data pipeline is our Kafka-based ETL that we developed in-house. Sri talked about it a little bit earlier. And you can check out our blog post about it, engineeringblog.yelp.com. And the distributed processing layer is how we do this at scale. MySQL is where the final data set is stored. And now this talk is largely about how we moved to doing this chain detection in Spark, you know, and how we migrated from Redshift. And let's first see how we did do it in Redshift. So we're going to have a more visual overview here. So the business data is replicated to a distributed file system with our data pipeline. Thank you, Sri. That is stored in HDFS. Our chain detector reads from data from HDFS, and with the help of Redshift, it executes a series of data transformations to generate our final data set. We then publish this data set to various clients. We version it in S3, so we can always revert to previous versions if there's a regression. Got the photo? Good. So just a little quick intro into Redshift, if you're unfamiliar. It's a relational data warehouse that allows you to run massively parallelized SQL queries against very large amounts of data. And you pretty much pay for it by the size of your data. So let's see how some parts of this was implemented before in the Redshift architecture. So before we can do anything, we need to actually put our data into Redshift, the data that we want to do transformations with. I have a Redshift client. We're going to actually create this table. This is all in Python. Then we'll simply ingest the data produced from our data pipeline into that table. Now let's do some pre-processing. So we have a bit of application logic. Given some chunk of businesses, we're going to produce some key value pairs, the business ID to the normalized name and its normalized URL. And these are just like the tokens that we saw before. We'll need a place to put these tokens, so we create the table, and we can do some computation on them later. Now we're going to grab all the businesses we want. And we only care about open businesses. And this query runs really fast, so that's no problem. Now we iterate over chunks of the result at a time. And we produce all the tokens for this chunk in parallel. And then store those back into Redshift. So some things to point out. First thing, there seems to be a lot of redundant I/O. We just uploaded a bunch of data from HDFS to Redshift in the last slide. Now we're downloading some of it back. We're uploading more stuff into a new table. Also, notice which logic is executed on this local machine versus the cloud. Just the SQL is massively parallelized. The Python is just locally parallelized, which is much slower. And it's not like we can do run this normalization function, getting the tokens in SQL because it can't be written in SQL. So we're kind of stuck there. And we're limited in what logic that can be run in the cloud. Lastly, doing this local parallelization is pretty distracting from the overall application logic. And it makes it harder to follow. Basically, we have all these pools littered everywhere. And as a developer, you want to focus on your application logic and how it all works. OK, so we're going to do stuff with our new tokens table. We're going to group the tokens just like what we did before. And we're going to compute some features. The pattern we're seeing here is that a lot of our logic is embedded in these SQL queries. And that isn't easily testable. Because this happens in a different place. This happens on Redshift. This doesn't happen locally. So I think we're starting to see a pattern here. So just some overview of the problems that we saw. So I found that the application is pretty complex because some logic is executed locally and some is in the cloud. Doing parallelization locally is limited. It can't be scaled horizontally because, well, it's local. And to make things faster locally was just messy and distracting, in my opinion. I have more problems. So with Redshift, we're using a shared cluster. That makes execution time a lot less predictable because many other users may be running intense queries just like us. And if you saw Sri's talk, you learned that we're already kind of hitting our limit in terms of scale here. For the same reason, it makes it difficult to estimate your spending. And with dealing with large amounts of data, it's a good idea to know your spending because it'll be a good benchmark when you actually reduce it. If your data is growing a lot, you want to make sure that your spending doesn't go out of control. As you saw, there is a lot of I/O overhead, which is just expensive and it's slow. So it's kind of alluded to testing earlier. For a large, complicated pipeline like Chain Detector, it's a good testing infrastructure is pretty crucial, essential for maintaining the quality of this data set. So I want to talk about testing. And with testing in mind, there's a lot more problems. So with this solution, our test would need to do a lot of mocking because we're relying on an external system. And when you have more mocking, there is more maintenance as a developer. If you decide you want one extra field from like your Redshift query, like instead of selecting this one field, you want more fields, not only your return value is going to be different, so not only are you updating your code, you're updating your tests as well. Every time. So that's more maintenance. And you're like, oh, well, hold on, you can solve that with integration testing. And yeah, we would need integration testing to do that because a huge chunk of our logic actually exists within those SQL queries that's executed elsewhere. But having good integration tests requires sandboxing, which means making sure you're reinitializing your state or your database before your tests. And Redshift isn't something you just install on your computer like you can with MySQL or Postgres. So this is actually pretty tricky to set up reliably. So that's how things used to be. Here's what we have now. Not much has changed. Well, the Redshift thing is gone, of course. And I changed that chain detector box, the chain detector component from a box to a cloud. We'll see why. So Spark 101, or I should say Spark ABCs. So Spark is a distributed processing framework. It's written in Scala, has official Python APIs. And there are many ways in Spark to express your data manipulations. You can use SQL. You can use a more functional API like map, reduce, filter, and so on. You can use data frames if you're familiar with pandas. You can handle a variety of input sources. You can read directly from HDFS or directly from the Cassandra nodes. You also typically run it in some standalone cluster or a shared cluster like Mesos. You can run it locally, which will be a huge win for us, as we'll see soon. You also have a lot more control over how much you pay because you would choose how much RAM and how many CPUs are appropriate for your application. So let's do this again. So here, we are reading from our data pipeline, just like before. A couple concepts. Spark context. This is like our gateway to the Spark execution engine. Number two, RDD. That's a resilient distributed data set. Distributed because the data lives across multiple nodes in the cluster, and it's resilient because it's fault tolerant. That's not a good explanation, is it? It's fault tolerant because if some partitions are missing due to like node failures, those will be recomputed, completely transparent to you. The RDD also provides us with APIs to execute transformations and actions on this data set in parallel. So our first one is going to be filtered just like before, where we remove closed businesses. Now we'll transform this into key value pairs. The key here is our name token, and the value is the business. Finally, we use reduce to aggregate all the businesses with the same name token. So all the businesses with the same name token will be in the same group. So yeah, we're concatenating these lists here. So one win here is that a lot of the parallelization has been abstracted from us, which allows us to focus on our application logic. And just like sanity check, does this look simpler than before? Hopefully. Just checking. Another thing to note is that like we're able to seamlessly combine our application logic with Spark. So how does that work? You can see that we are passing functions in the driver program to be run on the cluster, like this normalized business name function. So these are serialized and sent to all the executors, so this function can run against the data in that node. And the function can be pretty much anything. Like we do classification the same way. That's how we parallelize the classification. As long as that function like isn't stateful, you're good. A good example of a stateful function is like if you're like incrementing some global counter or something like that. So this looks much better. We saw less than 10 lines of code replace 2 whole slides earlier. But the hard part from before in the testing is that part of the application was in the cloud and like some of it was local, and like, I was kind of complaining that this would be hard to test. And now everything's on the cloud, so what does that mean for testing? So I alluded earlier that Spark can be run locally, and it works effortlessly with PyTest, which is a really awesome testing framework. And one thing to take care of is how to test this with like fake data and not like read from the production bucket. So to fix that, we want to create an abstraction for the file system. This is what we had before, which just assumed was we always want to read from the cloud. But we don't want to do this in our test environment. We want to run it on a really small data set in our test environment. So some proper abstraction is needed here. So we can introduce this data loader class that abstracts away where the data lives, and we can inject it into our Spark set. So we have one for HDFS, we have one for the local file system, and then we have like this sample Spark step. So this is a pretty common design pattern for more testable code. So for many tests, you need to initialize a bunch of things, of course. This is typically done in a setup method in most testing frameworks, of course. PyTest does it a little bit differently, perhaps a more powerful way that allows you to share code more easily. So these are called fixtures. So a couple concepts here. Spark context and the Spark session is like our gateway to executing Spark operations, and we want these available in our tests. So local 8 means we're running Spark in a local setting with 8 workers. And the scope session tells PyTest we want these fixtures available in all our tests. We're shared across all tests. So these will only be executed once. So let's see what a typical test looks like. I'm going to create a bunch of fake data, dump it to our local file system. Then in our test, we have an injected Spark context here. In our test, we just need to set up our local data loader, inject into a Spark step, and then simply run it. And then we get the results back, and we can do whatever assertions we want. Make sure it does the right thing. This simple short test just ran through like our long and complex chain detector pipeline. That is, ran through all the pre-processing, grouping all the tokens, merging, creating feature vectors, classifying. So the test covers like all of our application logic, tests the correctness of our Spark API calls, and even sanity checks our machine learning classifier. Like this is actually how simple our tests look for the chain detection system. And like when you just see a few lines of tests cover thousands of lines of code, like that's pretty awesome. It's really cool. So like, just like a before and after, quick summary, past and present. So on Redshift, we had like a lot of unnecessary data transfer between the cloud and the application. In Spark, we were able to read directly from HDFS. We saw that our SQL queries were massively parallelized, but we couldn't scale the local application. But everything is parallelized in Spark with the RDDs. Shared cluster in Redshift meant unpredictable speed and costs. And in Spark, we had more control there. In Redshift, doing unit or integration testing was a maintenance nightmare. And in Spark, it is stateless and no mocking or sandbox was needed. As a bonus, when we actually did this migration, before like we're focusing on any performance or tuning, like the Spark version was running 4 times faster. So let's talk about making our Python app ready for the cloud. So I think it's like pretty self-explanatory, like how we deployed our Redshift application, because it's like any regular Python application. We just need like a connection to Redshift. But now we're running everything on the cloud. So how do we do that? So we're running Chain Detector on AWS. And so we need to be compatible to Amazon Linux. Well, it's easy because Python is cross-platform, right? Well, not so fast. Many Python libraries are written in C and Fortran and need to be built for a specific platform. And PyPy may have pre-compiled wheels for us, but they may not exist for the platform you're going to run this on. So one way to deploy this is to zip up our repo, upload it to S3. We can provision our cluster, bootstrap it, install Python, and whatever else we need. Download our repo, build it, run it. Simple, right? The problem is with step 5 right here. So like I said, if a wheel doesn't exist, building certain libraries can take really long. You don't want to be wasting time building your app on really expensive hardware that we're using to run Spark. You'd also do this every single time, even if your dependencies don't change. And if something goes wrong during your build, you need to recreate your cluster all over again. I really like this logo. Anyway, Docker can probably help us here. So with Docker, we're actually going to build locally as if we were on Amazon Linux. And then we're simply going to cache that build. So here are some new steps. So in step 2, we build everything in a Docker container. And we only need to do that if dependencies change. So every time we create a new cluster, there's no additional building to be done. So that means we can change our application logic, have it immediately run once a cluster is provisioned, which is pretty great. So I hope this gives you an idea how you might deploy your existing Python app to the cloud and run Spark. So I've talked about how Chain Detector works, how we've migrated to Spark, and how a typical deploy looks like for a Python application. And you're probably wondering, how did it all go? Well, we did this migration without affecting the quality of our data set. There were no regressions, and we ended up with less code and fewer tests to maintain.
You mean no regression failures or no regression tests?
That's a good point. No regression failures. Lots of regression tests. We also ended up with a more scalable and easier to understand application. And I think that's just really important when you're onboarding the next developer to work on it. And this was just a really huge win for us, and we're super proud of it. And that's pretty much all I had to share with you today. Yeah, thank you very much.
All right, we have some time for questions.
That's where the fun begins.
Hey, thanks. Great talk.
Thank you.
I have a bunch of questions, actually.
I see you're reading from the laptop there. I'm really nervous.
So, do you only have production setting, or do you also have data scientists running ad hoc queries on your data on your Spark cluster?
Yeah, we also have data science.
OK, I'll talk to you about that afterwards. They also say Python is 10x slower than Scala when running Spark, since Yelp has a ton of data. I'm curious, how did you notice any slowdown? Does everything work nicely?
Yeah, we have some teams running Spark on Scala. We're using Python because a lot of this application was already written in Python. So migrating to Scala would be a huge, if it was 10 times faster, if that was really needed for this application, it could have been a good investment, but trade-off.
Cool. Thanks. And so you mentioned local testing, and we do that too. What we have noticed is when we do local testing, it works fine. When we deploy it on a large data set, the data has much more variability, and that always causes some tests to fail. Does that happen with you at all?
Yeah, a little bit. Something we can talk about after. Yeah.
Can you explain the Docker plus Spark configuration? Do you run Spark on top of some Docker orchestrates, Mesos, or something?
Oh, yeah, maybe that. So when I was talking about Docker, this was so we can actually build our dependencies for the Spark application, because we didn't actually want to do that on EMR. Does that make sense?
Great talk.
Thanks.
Just quick question about, did you evaluate using Dask for this purpose? Did that come up during the?
Oh, sorry.
Did you try using Dask or evaluate using Dask?
I'm not familiar.
Dask is task parallelism, gives you the same capabilities, but more.
Oh, yeah, sorry, I misheard, no.
Dask is in memory too. Yeah.
No, we didn't.
Okay,
Yeah.
fair enough. Have you, and also for the deployment side, have you tried using like a conda package or conda environments to simplify the production of lots of
Yeah,
binaries?
like, so like, this was kind of done like as like we were like Spark was like, we're like an early adopter team for it, and like some of that like tooling didn't quite exist yet, and more teams have like already moved to that as well. Yeah.
I have a question. How long did you plan for this migration to take, and then how long did it actually take?
Just curious.
That's a good question. So this happened late last year. I think planned for it for about a quarter, took almost two, about a quarter and a half. A lot of it had to do with like understanding like a lot of the existing application logic, because myself and the folks working on this, we did not originally develop the original application logic that was like working with Redshift. So like there was a lot of like ramp up there, and like, yeah, so there's that took a lot of extra time. Yeah.
All right. Thank you very much.
Thank you.